Right now, as you stand completely still, your head is aging slightly faster than your feet. That sounds impossible. Our daily experience suggests that time is universal, a rigid backdrop to reality. For centuries, the most influential minds in science agreed. In his 1687 Principia, Isaac Newton formalized the concept of absolute time. He argued that time flows equably, without regard to anything external, a cosmic clock ticking at the exact same rate everywhere in the universe. That model held until 1905, when Albert Einstein proposed a different architecture for the universe. He argued that space and time are a single, woven, flexible fabric. Einstein theorized that the pace of time is uniquely yours. How fast your personal clock ticks depends on your speed through space and the strength of the gravity pulling on you. But math on a chalkboard is one thing. To prove that time can actually bend, physicists had to take the most precise clocks ever built and put them in motion. To understand how they proved it, we have to look at Einstein's two mechanisms for warping time. The first comes from special relativity. Moving at high velocities slows down the passage of time. Physicists illustrate this using a light clock, where a beam of light bounces between two mirrors. If the clock is stationary, the light bounces straight up and down. But if the clock moves sideways, the light travels a longer, diagonal path to hit the opposite mirror. Because the speed of light in a vacuum never changes, that longer distance creates a problem. To keep the speed of light constant, the clock itself has to tick at a slower rate than a stationary one. General relativity introduces the second rule. Gravity is the physical warping of spacetime by massive objects. This means that the deeper you are in a gravitational well, closer to a massive object like Earth, the more spacetime stretches, and the slower time passes. Combine these two rules, and time loses its status as a universal constant. It becomes a localized, bendable property that changes depending on where you are and how fast you're moving. By 1971, technology had finally caught up to these equations. Physicists Joseph Hafele and Richard Keating set out to physically test time dilation using ultra-precise atomic clocks. They didn't use a specialized rocket. Instead, they bought tickets on standard commercial airliners, strapped their atomic clocks into passenger seats, and flew them around the world. They flew one set of clocks eastward, moving with the Earth's rotation, and another set westward, flying against it. Because of the Earth's spin, the eastward clocks had a higher absolute velocity than the westward ones. After their flights, they brought the airborne clocks here, to the United States Naval Observatory, to compare them against stationary reference clocks that had remained on the ground. This table compares their predictions against the results. The airborne clocks gained and lost fractions of a second that matched Einstein's equations to within the expected margin of error. With a few plane tickets and cesium clocks, time dilation shifted from an abstract equation into a measured physical fact. Following that success, physicists began measuring time dilation on increasingly smaller, more terrestrial scales. Researchers took atomic clocks up mountainsides, recording that time passed slightly faster at a high-altitude summit than it did in the valleys below. By 2010, the instruments had become so sensitive that physicists at NIST measured gravitational time dilation across a height difference of just 33 centimeters, about 1 foot. And in 2024, using optical lattice clocks, researchers successfully recorded the warping of time across a sub-millimeter gap. They proved that time ticks at different rates across a distance the width of a human hair. This reveals that the warping of spacetime is a continuous physical gradient woven through every inch of our world. If we ignored relativity today, a massive piece of our modern infrastructure would break down. Global positioning satellites move at immense speeds while experiencing weaker gravity than we do on the surface. These competing forces cause their onboard clocks to run at a different rate than ours. If engineers didn't continuously correct those orbital clocks using Einstein's equations, the resulting timing errors would cause GPS navigation to drift by miles and fail within minutes. Which brings us back to your head aging faster than your feet. It's a microscopic difference, proving we exist inside a dynamic, bending environment. Absolute time is a myth. The universe is a pliable fabric, and every object, every satellite, and every person is traveling through it at their own unique pace.